The average McDonald's restaurant generates $2.1 million in sales each year, with a standard deviation of 0.8. Victoria wants to know if the average sales generated by McDonald's restaurants in Indiana is different than the worldwide average. She surveys 33 restaurants in Indiana and finds the following data in millions of dollars. Okay, so we have the data here, and we want to perform a hypothesis test using a 4% level of significance. Okay, so we know that we are dealing with average, so we know population mean is what we are hypothesizing on. And the average McDonald's restaurant generates $2.1 million in sales each year. And Victoria wants to know if the average sales generated by McDonald's restaurants in Indiana is different than the worldwide average. Okay? So, the average sales McDonald's restaurant generates $2.1 million in sales. So the average sales is $2.1 million. So notice it's not is at least $2.1 million. It's not more than $2.1 million. It generates exactly $2.1 million. So our average is $2.1 million. Now, in this case, all our data is already in millions of dollars. So we are just going to leave it in this form. And we understand that 2.1 really means $2.1 million, okay? But it matches this data we have, which we are told is in millions of dollars, okay? Okay, and we want to know if the average sales generated by McDonald's restaurants in Indiana is different. So different could be less than, but it could also be greater than, right? So to encompass both of those, we just want to say it's different, so it's not equal. We want to see if it's not equal, okay? Since this guy has an equal symbol, this is our null. Since this guy does not have an equal symbol, this is our alternative. Okay, so we have as our null, the mu is equal to $2.1 million. And as our alternative, we just want to see if it's different from $2.1 million. Okay. Now our alternative hypothesis tells us what kind of test we are using. In this case, since we're just want to be not equal to 2.1, that means we could go on the left side or the right side, right? To the left or the right, we are still not equal to 2.1. It doesn't matter which side we go on. So it's not just a left tail test or a right tail test. We want a two-tailed test. We want a two-tailed test because both tails are away from that mean of 2.1 that we are hypothesizing. Okay? Okay, step 2. Assuming the null hypothesis is true, determine the features of the distribution of point estimates using the central limit theorem. So by the central limit theorem, we know the point estimates are either normally distributed or t-distributed. Now, if we know the population standard deviation, then the answer is normally distributed. If we don't know the population standard deviation, we have to estimate that using a sample standard deviation and a t-distribution. Okay, but in this case, we do know the population standard deviation. It tells us right here, this with a standard deviation of 0.8. Okay, so in this case, we can use a normal distribution for this, for the distribution of sample means. Okay, so the mean of this distribution of sample means, so by the central limit theorem, just as a reminder, the mean here the distribution of sample means is normally distributed with a mean mu sub x bar of mu, or sometimes we say mu sub x. It's the population mean, okay? And sigma sub x bar is, so since we know the population standard deviation sigma, we just use that and then divide by square root of n, where square root of n is our sample size. Okay? So let's find these guys. So remember, by the way, that this guy, that's what we hypothesize, right? And we are assuming that hypothesis is true so we can test it. So our null hypothesis says the population mean is 2.1, so that is going to be our distribution mean. Okay? And for the distribution standard deviation, we're going to take our population standard deviation, that's our sigma, and we're going to divide by the square root of n, which is our sample size, which we are told right here is 33 restaurants. Okay? So population standard deviation sigma is, what was it, 0.8? And the sample size is 33. We're looking at 33 restaurants. So sigma sub x bar is going to be sigma, our population standard deviation, divided by the square root of n, our sample size. And let's write that one more time so we'll actually get to see the result. Run it. And there we go. That is our distribution standard deviation. Okay? And so now that's step 2 done. We know what kind of distribution we're dealing with. We know how our point estimates, our sample means, are distributed. Okay, so now we can find the p-value of our particular point estimate for our sample. So since we are estimating, since we are performing a hypothesis on the population mean, we estimate it with a sample mean, which we notate with x bar. Okay. Now this is a two-tailed test, but to find the probability, we initially need to pick a tail. And which tail that we are going to start with depends on our point estimate. So we actually need to find our point estimate. Now we have all this lovely data. We need to find our point estimate, which is our sample mean. Our sample mean estimates our population mean at a particular point. So let's copy this data, and let's find our sample mean. So all our data, I'll store it in X. Paste all that data in there. Got a parenthesis at the end already. Okay. And so I'm going to find X bar now. And all I need to do to find the mean of these is add them up and divide by how many there are. And I found n earlier, right? Let's write it one more time to print it out. Okay. There is our sample mean. Okay, so what we're going to do here, in this case, since it's a two-tailed test, and since our point estimate is larger than our hypothesized population mean, we're going to find the area in the tail that's closer to our point estimate first. So in our case, we're hypothesizing the population means 2.1, and we've got a sample mean of 2.25 about. Guess rounding it's about 2.26. Okay. Because it's up here, and because we're doing a two-tailed test, we're going to start with whichever tail our point estimate is closer to. So in this case, we're going to start with the upper tail. Okay, and you're noticing I'm saying start. We will have to take into account this other tail in a moment. Okay, but for now, let's start with the upper tail. In this case, since that's where our point estimate is closer to. Okay, so I'm going to now need to convert, in this case, to a z-score, because in this case our data is normally distributed, so I'm converting to a standard normal distribution. Okay. Oh, and because we're doing upper tail, we're going to start by finding the probability that we're bigger than this value, right? So z is greater than or equal to, and now I need the z-score of my point estimate, my sample mean. So my z-score of my sample mean is z equals x bar, my sample mean, minus mu sub x bar, the mean of my distribution of all sample means, over sigma sub x bar, my standard deviation of the distribution of all sample means. And you'll remember that this guy is just the population mean mu. Okay? Now, looking back up here, I notice that I haven't actually used my population mean yet, so I'm going to start by adding that in there. And my population mean by hypothesis is 2.1. So 2.1. And I think I got everything else I need. So my z-score is going to be my point estimate, in this case my sample mean, minus my hypothesized population mean, mu, divided by the standard deviation of my distribution of sample means. So that would be sigma x bar. Don't confuse it with your population standard deviation sigma. We're not finding the probability of the population, we're finding the probability that we get a sample mean that is more extreme than the one we got. So I'm going to divide by sigma sub x bar. Okay? And that's going to give me my z-score. So let's see what that is. So our z-score is 1.131 about. So let's copy, paste that in. Okay. So now that we got our z-score, we can actually find this probability using the p-norm function, since we know we have a normal distribution. So p-norm, plug in my z-score, and I need to decide on lower tail. In this case, since I'm looking at the probability of getting a sample mean bigger than 2.257, so bigger than this, I do not want the lower tail, right? I'm looking at just the probability in the upper tail. So lower tail, false. Okay. And, well, let's just see what that is first. Okay. So that's the probability. However, this is not quite the p-value. Because we are doing a two-tailed test, we also have to think of what would happen if we got a value as extreme in the other tail. Okay? So what we have just done, actually, is we found just the probability in this tail, which is only half the p-value. The other half of the p-value lives over here. And together, they give us the full p-value. But notice that each is a perfect half of the p-value. So if we know only half of it, and we do, we just found this half over here. If we know only half of it, we can find the other half by just multiplying it by 2, by just doubling it, right? So that's what we are going to do to actually find our p-value. Okay, so now that we have the probability, I think I'll call this variable prob, or maybe half p-value, whatever you want to call it. Okay, I'm going to run it one more time to make sure it actually stores the variable. Let's have it continue to print out so we can see it. Okay, now we're going to multiply it by 2, and that's going to give us our full p-value. Okay, and I'll type it one more time so we can see the results. There we go. That is our p-value. Okay. So when it's a two-tailed test, and only when you're doing a two-tailed test, whatever probability you end up getting, you need to double it to get the p-value. Okay. I should also mention in this case, we found the area in the upper tail because our point estimate was bigger than our hypothesized population mean. Now, if this was smaller, if this was like 1.9, if our point estimate was smaller, we'd actually go to the upper tail. We would look at, or I'm sorry, the lower tail. We would get the area in whichever tail this guy's closer to. So a two-tailed test is a little bit more involved than just a left tail test or a right tail test, because you have to think a little bit more, okay, where is my point estimate? Once I get that probability, you have to remember to multiply by 2. Okay, so be careful with those two-tailed tests. Okay, but we got our p-value now, so just copy that one more time, because that is how I start step 4. Right? I need that p-value. So since the p-value equals 0.2578, and I want to now compare it to my alpha. My alpha, we are told up here, is that we are performing a hypothesis test using a 4% level of significance. So that's my alpha. So 0.04. That's the threshold below which I'm comfortable in saying that this is such an unlikely event that it's more likely that our null hypothesis is not true. But in this case, our p-value is greater than or equal to our alpha. So we have a higher probability of something as extreme as what we have occurring. It's not all that uncommon, right? This is about 26%, which is much larger than 4%. So we will not reject the null hypothesis. There's just not enough evidence to be able to say that the null hypothesis is probably false. Okay, so since we cannot reject the null hypothesis, now let's interpret that result in the context of our problem. Either we cannot conclude that the mean sales of McDonald's restaurants in Indiana differs from the average McDonald's sales worldwide, or we do conclude that the mean sales of McDonald's restaurants in Indiana differ from average McDonald's sales worldwide. Well, we can't reject the null hypothesis. And the null hypothesis says that the mean in Indiana matches what's happening in the rest of the world. So we cannot conclude that the mean sales of McDonald's restaurants in Indiana differs from average McDonald's sales worldwide. Okay, so let's submit it, and we have it.